Right now, somewhere above you, a 400-ton machine is hurtling through the sky at 900 kilometers per hour. Inside its wings, not under the hood, not in a tank bolted to the fuselage, but inside the wings themselves, there are up to 180,000 liters of fuel. And that fuel is kerosene, not gasoline, not diesel, not some exotic aerospace compound with a classified name. Kerosene, the same substance that lit lanterns in the 1800s. The same stuff your grandmother might have used in a space heater. And the moment most people hear that, they ask the same question. Why? Gasoline is more powerful. Gasoline is everywhere. Gasoline runs every car, every motorcycle, every lawnmower on the planet. So why are the most advanced flying machines ever constructed burning lamp oil? The answer isn't what you expect. It involves vapor bubbles that can kill an engine mid-flight, a temperature that turns fuel into candle wax at 40,000 feet, and, this is the one that stops people cold, a second job that jet fuel is doing inside the engine that has nothing to do with burning at all. Stay with me to the end, because that last point will permanently change how you think about aviation. Let's start by dismantling the obvious assumption, because almost everyone gets this wrong on the first try. The instinct is logical. Gasoline must be too weak for aviation. Planes are massive. They need serious energy. So engineers must have found something more potent, more refined, more sophisticated. The reality is the exact opposite. Gasoline wasn't rejected from aviation because it lacks power. It was rejected because under the specific conditions of high-altitude flight, it becomes genuinely dangerous to use. Here's why. At cruising altitude, roughly 10,000 meters above sea level, atmospheric pressure is about 26% of what it is on the ground. And at that pressure, liquids behave in ways that seem counterintuitive down here at sea level. They evaporate faster. They change from liquid to vapor at lower temperatures. They become, in engineering terms, more volatile. Gasoline already has an extremely low flash point, around -43 degrees Celsius. That means gasoline is producing ignitable vapor at virtually any temperature a human being has ever experienced. At altitude, with pressure dropping and temperatures falling, gasoline evaporates aggressively inside the fuel lines. And when that happens, you get vapor bubbles. Pockets of gas trapped inside what's supposed to be a continuous stream of liquid. Engineers call this vapor lock, and the name is exactly what it sounds like. Imagine drinking through a straw, but someone keeps punching air holes in the middle of it. The fluid doesn't flow smoothly anymore. The suction breaks. The stream sputters and stops. Now replace that straw with the fuel line feeding a jet engine over the Pacific Ocean. A jet engine requires a continuous, uninterrupted flow of liquid fuel to maintain combustion. When vapor lock disrupts that flow, combustion becomes unstable. The engine surges and stutters. In the worst case, it flames out entirely. At 40,000 feet, over open water. This is not a theoretical risk that engineers model on paper. Vapor lock is a documented failure mode, and it was one of the defining problems that early aviation engineers had to solve before long-range flight was even possible. Gasoline didn't fail the audition because it was weak. It failed because, at altitude, it becomes unpredictable in exactly the ways you cannot afford. Now let's talk about fire. There's a demonstration that gets done in aviation engineering programs. An instructor holds a lit match over an open container of jet fuel and drops it in. The match goes out. The fuel does not ignite. Do that with gasoline, and the result is a fireball. This isn't a trick. It's chemistry, and it comes down to one number: flash point. Flash point is the lowest temperature at which a substance produces enough vapor to ignite when exposed to a spark or flame. Gasoline's flash point is -43 degrees Celsius, well below freezing, well below any temperature you're likely to encounter on a normal day. Gasoline is, in almost every real-world scenario, already producing ignitable vapor just sitting there. Jet fuel's flash point sits between 38 and 72 degrees Celsius, depending on the grade. You have to actively heat jet fuel before it becomes ignitable. At room temperature, in open air, it is surprisingly resistant to catching fire. Now scale this up. A Boeing 787 flying from Los Angeles to Sydney carries roughly 100 tons of fuel. That's not a typo. 100 tons. That fuel represents nearly a third of the aircraft's total takeoff weight. The wings are, in a very real sense, flying fuel tanks with engines attached. If that fuel had gasoline's ignition characteristics, then any spark from a static discharge, any electrical fault in the wiring, any friction from structural stress during turbulence, any of those events could trigger an ignition chain inside a fuel tank holding the equivalent of a small oil depot. Kerosene's high flash point doesn't just reduce risk. At aviation scale, it is the difference between an emergency that crews can manage and one that nobody walks away from. Here's the one most people have never thought about, and it reframes the whole conversation. We've talked about what happens when fuel gets too volatile. Now let's talk about what happens when it gets too cold. Outside a cruising airliner, the air temperature is typically between -50 and -60 degrees Celsius. That's not a typo either. -50 to -60. The metal skin of the aircraft, including the wings where all that fuel is stored, conducts that temperature directly into the tanks. And at those temperatures, most common fuels don't just flow slowly. They solidify. Paraffin wax crystals begin forming inside the fuel. The mixture thickens from liquid to slurry to something approaching gel. The fuel lines, which rely on gravity and pump pressure to deliver a continuous flow, become progressively obstructed. And an engine that can't draw fuel from its own tanks produces zero thrust. Standard jet fuel, grades called Jet A and Jet A1, is specifically engineered to remain fully liquid down to -47 degrees Celsius. This isn't accidental. Chemical additives are introduced during refining that actively suppress crystal formation. The molecular structure of the fuel is refined to maintain flowability at temperatures that would turn most other fuel types into a waxy paste. This is why calling jet fuel kerosene in the casual sense is a little misleading. Your great-grandfather's lamp kerosene and the fuel in a modern Airbus share a lineage. Both come from the same fraction of crude oil. But they are not the same product. Modern aviation fuel is a precisely engineered aerospace material. It goes through refining and additive treatment specifically to hit thermal performance targets that basic kerosene could never meet. The fuel in those wing tanks has been designed, tested, and certified to perform in conditions that exist nowhere on the surface of the Earth. Here's a number that tends to surprise people. From a standard barrel of crude oil, only about 10% of it meets the specifications required for jet fuel. A barrel holds roughly 159 liters. After fractional distillation, the process where crude oil is separated into its different components by boiling point, after refining, after additive treatment, after quality certification, you get approximately 15 to 16 liters of jet fuel per barrel. The other 90% becomes gasoline, diesel, heating oil, plastics feedstock, liquefied petroleum gas, and dozens of other products. 10%. That scarcity has consequences that ripple through every layer of the aviation industry. Fuel typically represents 20 to 30% of an airline's total operating costs. Not fuel and labor. Not fuel and aircraft leasing. Fuel alone. 20 to 30 cents out of every dollar a passenger pays for their ticket goes toward covering the cost of a substance that makes up a single-digit percentage of what comes out of a barrel of oil. This is why every generation of commercial aircraft represents an obsessive engineering effort to squeeze more range out of every liter. The fuel efficiency gains between a Boeing 707 from the 1950s and a Boeing 787 today aren't marketing statistics. They're the compounded result of decades of engineering driven, in no small part, by the economic pressure of operating on a fuel that is inherently constrained in supply. When an airline announces that a new aircraft model is 20% more fuel efficient, that number translates directly into hundreds of millions of dollars across a global fleet operating over decades. That's how tight the economics are. That's how much the 10% yield matters. This is the part that changes how people think about this subject. And it's the part that almost never gets discussed outside of aerospace engineering programs. Inside a jet engine, the combustion chamber and the turbine section that follows it operate at temperatures exceeding 1,000 degrees Celsius. Some modern high-performance engines push well beyond that. At those temperatures, without active thermal management, The metal components would deform, crack, and fail within minutes. Modern engines handle this through multiple cooling strategies. Air is bled from the compressor and circulated around the hottest components. Turbine blades are cast with internal cooling channels. And then there's the fuel. Before jet fuel ever reaches the combustion chamber to be burned, it is routed through a series of passages that run alongside the hottest sections of the engine. The fuel, which is still relatively cool at this stage, absorbs heat from the surrounding metal as it flows through. It draws thermal energy away from components that would otherwise overheat and carries that energy with it into the combustion chamber, where it's released as part of the burn. The fuel is doing two completely separate jobs. On the way in, it's a coolant. It's thermal management. It's the reason the engine doesn't destroy itself within minutes of startup. On the way out, once it reaches the combustion chamber, it ignites and becomes the power source. This is called using the fuel as a heat sink, and it is not a minor design detail. It is a fundamental part of how modern jet engines manage the thermal loads that make them so powerful. Now here is why this matters for our question. This function, using the fuel as a coolant before burning it, demands a very specific set of properties. The fuel has to remain thermally stable when it gets hot, so it doesn't break down chemically before it reaches the combustion chamber. It has to have the capacity to absorb significant heat without vaporizing prematurely. It has to flow reliably at the temperatures and pressures inside the engine. Gasoline fails this requirement. It's too thermally unstable. It starts to break down and vaporize at temperatures well below where jet fuel remains stable. If you tried to use gasoline as a coolant in a jet engine, you'd get fuel decomposition, coking, carbon deposits clogging the cooling passages, and eventually a catastrophic failure. Jet fuel, with its higher flash point, its thermal stability, and its molecular structure, handles this thermal cycling without breaking down. It absorbs the heat. It carries it to the combustion chamber. It burns cleanly. Nothing else commonly available does all of that. The next time you're walking through a jetway and you catch that smell, that distinctive, slightly medicinal kerosene scent that anyone who flies regularly knows immediately, you're not smelling leftover industrial waste. You're not smelling a century-old technology that the industry never got around to updating. You're smelling a substance that was engineered to resist ignition until the exact moment it's supposed to ignite. That stays liquid at temperatures cold enough to freeze most industrial fluids solid. That flows steadily through fuel lines at altitudes where gasoline would vapor lock and die. That cools the engine components it's about to burn inside. That was drawn from a fraction of crude oil that takes the entire modern petroleum industry to produce correctly. What started as lamp oil in the 1800s became, through a century of relentless engineering, the substance that makes it possible to board a plane in Los Angeles and land in Tokyo 11 hours later. That's not a story about kerosene. That's a story about what happens when engineers refuse to accept the world as it is and keep pushing until the ordinary becomes extraordinary.